Today we're going to talk about proof by contrapositive. Now when we talk about the contrapositive, we're talking about the implication not Q implies not P, when the original implication was P implies Q. So if I have the implication, if 3 is odd, then 57 is prime, the contrapositive of that is 57 is not prime. So if 57 is not prime, then 3 is not odd, or 3 is even. And if we construct a truth table to take a look at the contrapositive, we end up finding that the two columns are equivalent. They are both only false when P is true and Q is false. And because of that, we have a theorem that's going to be a super useful theorem for us, that the original implication and its contrapositive are logically equivalent. What this means for us is that if we have some implication that we're trying to prove, P implies Q, and we're really running into some problems along the way, then we can take a look at the contrapositive. Not Q implies not P. And it might be that it's easier to prove the contrapositive. Since the two are logically equivalent, proving either one also proves the other statement. So when we talk about the proof by contrapositive, what we're talking about is the direct proof of the contrapositive of the original implication that we were attempting to prove. So let's take a look at an example where a proof by contrapositive is a helpful tool for us. So let's say we have an integer x, and if 5x minus 7 is even, then x is odd. So we want to show if 5x minus 7 is even, then x is odd. Now we could say let 5x minus 7 be even and then use the definition of even, but then we have a really complicated equation set up with multiple variables in it. On the other hand, if I say let x be odd, then I have a really simple equation. So in this case, the contrapositive says if x is even, then 5x minus 7 is odd. I encourage you to write that down so that you know what you're trying to prove as your new implication. So we're going to assume that x is even. So we have x is equal to 2a for some integer a. Now we can plug that into 5x minus 7, and we can do some manipulation, and we end up finding out that we have 2 times 5a minus 4 plus 1. And 5a minus 4, a was an integer, so that's a combination of integers and an integer itself, therefore. So we have, by definition, that 5x minus 7 must also be odd. Hold on to this result, we're going to use it later, so I'll reference it back. Now let's take a look at another example. So say we have a biconditional that we're trying to prove. Namely, for x an integer, 11x minus 7 is even if and only if x is odd. So there's two implications we need to prove for a biconditional. We need to prove that if x is odd, then 11x minus 7 is even, and we need to prove that if 11x minus 7 is even, then x is odd. Now the first of those, if x is odd, then 11x minus 7 is even, is relatively easy to do as a direct proof. So by definition, x is odd gives us x equals 2r plus 1 for some integer r. We can plug that in and we end up with 2 times some integer. So therefore 11x minus 7 is in fact even. The second part of that looks a lot like our last example, where we had something more complicated we would be assuming if we went with a direct proof, whereas if we go with the contrapositive, we get to just assume that x is even. So instead of going with proving this directly and the more complicated way, we're going to go with the contrapositive. So we're going to assume that x is even, and we're going to plug in 2s for some integer s for x, And we're going to work this out, and just like in our previous example, we're going to find that it must be odd. So since we've proven both implications, we have now proven the biconditional. So whenever you see a biconditional, you need to remember that there are two proofs that you need to complete. This result is a biconditional, and it's a very important one. And we said that when we have a very important statement that needs to be proven to be shown to be true, we're going to call it a theorem. So we're calling this a theorem rather than a result. It's just an important result, though. So this is for any integer x. We have x squared is even if and only if x itself is even. So it's a biconditional, and we need to prove both implications. The if x is even, then x squared is even, and if x squared is even, then x is even. And you can see that we've done both. And again, we use the contrapositive for the if x squared is even, then x is even. Finally, I said that we were coming back to that previous one we had. So let's say we set out to show that if 5x minus 7 is odd, then 9x plus 2 is even. Both the P and the Q statement here involve equations and are a little bit more complicated than we'd like to deal with. So remember, we already showed that if 5x minus 7 is odd, then x is even for all integers x. And since we have that result, we can use it. And whenever we have a result we can use like that, it's called a lemma, that result is. So we're going to use the lemma and say that we're letting 5x minus 7 be odd. Then by our lemma, x is even. So now, since x is even, x is going to equal 2 times z for some integer z, and we can plug that in. And when we plug that in and we do some simplifying, we have 2 times 9z plus 1 is equal to 9x plus 2. And therefore, 9x plus 2 must be even.